So now we're going to look at the shapes of molecules, and the theory we're going to use here is VSEPR theory. That's an abbreviation for valence shell electron pair repulsion theory, and it's not exactly VSEPR, but that's close enough pronunciation. It's just too long to say. So this is based on the idea that electron groups will repel each other. And it's a very simple model for molecular shapes, and it works really quite well. So the idea here is that around the central atom, there are electron pairs, or electron groups specifically. And these electron groups repel each other. They take up space and they push each other away. So it's important to understand what an electron group is. An electron group would be a lone pair, a single bond, a double bond, a triple bond, or a single electron. So we sometimes slip and say electron pairs, but they are electron groups. So we look at the repulsions between the electron groups on interior atoms, and that will determine the molecular geometry. In preferred geometries, you're going to have a maximum separation of those electron groups because that will be a minimum energy. And everything's trying to go to lower energy. So if we look at the Lewis structure for beryllium chloride, we've got beryllium in the center, and we've got a chlorine on each side. And we have to have at least single bonds there. And then between the two chlorines, there's 14 valence electrons, and the beryllium has 2, so it's a total of 16 electrons. So we put those around, we had 2, 4, 6, 8, 10, 12, 14, 16. This structure does not obey the octet rule. Is that okay? Yeah, because beryllium is one of those smaller elements. And so it sometimes has an incomplete octet. If we look at formal charges for this molecule, we'll find that they're all 0. So when we look at the Lewis structure, we look at the central atom and we see that it has 2 electron groups, the single bond and that single bond. Those 2 electron groups are going to try to get away from each other. So they are attached to the beryllium, so they can't just leave, but they could be different places around the beryllium. And so, I like to make things more personal. So I think of this as maybe this is you, and this is your ex, right? That person who just broke your heart or ruined your life or whatever. This is the earth. You're on one side, and you'd like that person to be on the other side of the earth, right? As far away as physically possible, right? So these 2 electron groups repel each other. They're going to get as far away as possible. And for 2 groups, that means that they're on opposite sides of the central atom. So we can talk about a bond angle, which is the angle formed by this electron group to the central atom to the other electron group. These are in a line. That angle is 180 degrees. So we're looking for the largest bond angle that we can have, and there you can't get any larger than that. So this is called a linear geometry because the 3 atoms are in a line, and the geometry is confirmed by observation. Any questions? Let's look at carbon dioxide. So if we draw the Lewis structure for carbon dioxide, and there's good reason why we talked about Lewis theory first. We need to be able to draw Lewis structures in order to be able to do VSEPR theory. We'll end up with this. The carbon has 2 double bonds. The oxygens each have 2 lone pairs, and if we do formal charges, they're all 0. What we're looking at is the number of electron groups on the central atom. We do not care about these lone pairs on the oxygens. We're just looking at the central atom. Remember, an electron group is a pair, a lone pair, a single bond, a triple bond, a double bond, or a single electron for a free radical. So this double bond is one group, and this other double bond is the second group. So two groups get away from each other by being on opposite sides of the world of the central atom. And so this will also have a 180-degree bond angle and have a linear geometry. Any questions? If we draw the Lewis structure for BF3, it's like some friend group or something. Best friends forever and ever. Boron. Oh, yeah, I need a pen. Choose a pen. So boron and 3 fluorines. And we would discover that the fluorines all have octets and the boron does not. And that's okay because boron sometimes does that. We look at the central atom here and we count the number of electron groups, and there's 3. And so 3 things will move away from each other. The maximum angle that they can achieve is 120 degrees. And so this is called a trigonal planar geometry because it forms a triangle and it's flat. It's in a plane. If we look at something like formaldehyde, here the Lewis structure has been drawn for us. Look at that central atom. How many electron groups? Not pairs, but groups. This double bond is one group. As this double bond is between the oxygen and the carbon, and those 2 bonds cannot move away from each other, right? They're stuck together. So that's 1 group, 2 groups, 3 groups. So even though this carbon has a double bond and 2 single bonds, it does have an octet, it still has 3 electron groups, and those 3 electron groups will separate and form a trigonal planar geometry. What's a little bit different here is the angles are slightly off. They're not all 120, and that's because this one is a little more repulsive. It takes up more space. And so these 2 guys say, well, I'd rather be a little closer to you if that means I can be further away from him. So the angle here is a little more than 120, and here it's a little less than 120. It's because of the double bond. It kind of makes sense. A double bond is twice as many electrons. It probably takes up more space. Any other questions? So I actually have the balloons here, but there are also pictures of balloons in the textbook and on the slides. So here we've got the 2 balloons. They naturally go opposite each other. You put a 3rd balloon in there, and they form this triangle, and it's planar, it's flat. Putting a 4th balloon in there is a little harder to visualize. And so let's look at what happens when we put another balloon on there. It's important to remember the balloons are representing the electron groups, not the atoms. So we put that 4th balloon in, and we get a 3-dimensional thing now. It's not in a plane. It's called a tetrahedron or a tetrahedral geometry. The bond angles here are 109.5. It's a little harder to understand because in a sphere, you don't have just the 2 dimensions anymore. Thankfully, we don't really need to understand that. So these, the balloons are going along separated 4 things. That just didn't come out very well. Like the corners of the tetrahedron. There's 4 corners. You could also call this a trigonal pyramid, but we use trigonal pyramid for a different shape because here we're looking at the central atom in the middle and those electron groups going out in 3 dimensions. So if we look at methane, here's the Lewis structure for methane, 4 electron groups around the central atom. When we draw Lewis structures, we do use right angles. because Lewis structures are two-dimensional. They're on a piece of paper, they're on a screen. This represents the connections of the atoms, but it doesn't represent the shapes of how they're arranged, the angles, the shape of the molecule. So this is the shape of the molecule. It's a tetrahedral geometry. That's the one I just made, yeah. And so this is made using a ball and stick model. So we look at the Lewis structure like this, and then we understand that in three-dimensional space it does that. What if we stick another balloon in there? So when we add a fifth balloon in there, that is going to push the other balloons a little closer together. The name of this shape is Trigonal Bipyramid, because we have this triangle in the center with a pyramid on each side. So it's a double pyramid that has a triangular base. The ball and stick model kind of opens things up so we can see what's going on a little better. Here's our central atom. In this case it's phosphorus, and it has 5 chlorines around it. So there are 5 electron groups. They're each single bonds. And the best they can do here is to have 3 of them lying in a plane with angles of 120, and this one sticking up and that one sticking down. So we have 2 different bond angles in this shape. We have 90 degrees between the axial chlorine and the equatorial chlorine, and 120 degrees between adjacent equatorial chlorines. Does that make sense? So we have the axis and the equator. The octahedral geometry, we add in another group. So we add in another balloon, and that's going to push the remaining balloons, the previous balloons, closer together, and we end up with what's called an octahedral geometry. This makes an octahedron. So it has 6 points. Around the center, we can envision these 4 that have 90-degree angles, and that would be the equatorial and the axial positions above and below, but these also have 90-degree angles. So in the octahedral structure, all the bond angles are the same. Yes?
There's only 6 angles. Why is it called octahedral?
That's an excellent question. Why is it called an octahedron? Because there are 8 sides. If you look at the triangles here, there's 4 on top and 4 on bottom. There's 8 sides. Yeah, that's an excellent question. A tetrahedron has 4 sides. A cube has 6 sides, but it's not called a hexahedron. I guess you could call it that, but nobody does. When we draw the Lewis structure for this, we've got this S sulfur in the middle. Lewis structures are flat, and so we just spread them all out like that. And then we have to kind of interpret in our minds that we understand this is supposed to be representing something that's three-dimensional. This geometry and the trigonal bipyramid only happen when you have an expanded octet on that central atom. So let's determine the molecular geometry of carbon tetrachloride. The first step is drawing the Lewis structure. So we've got 1 carbon and 4 chlorines. So we'll start by just putting the chlorines around the carbon. We always have to count out the number of electrons. So 4 on the carbon. There's 4 chlorines, they each have 7. So that's 28 and 4 is 32 electrons. We have 2, 4, 6, 8 in the bonds. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So everybody can have an octet with only single bonds. that's the starting point for applying VSEPR theory. What we're going to do is we're going to look at the central atom and ask ourselves, how many electron groups are attached to the central atom? 4. There's 4 single bonds. And so then we think, well, what do 4 balloons do when we tie them together? What shape do they make? The tetrahedron. So the molecular geometry here is tetrahedral. Now, drawing these 3-dimensional shapes can be challenging. So you would draw the things that lie in a plane first, and then we have to indicate somehow that there's some that are out of the plane. And so this one over here, we can see where it attaches to the central atom. And this one back here, we can see where the bond attaches to that. And so that gives us an illusion of a 3-dimensional structure. We don't usually draw pictures like this because it's a bit tedious. And so we've come up with a way of representing these just mostly with lines and letters. And so we would represent this carbon as a C, and then we're going to put the 2 that are in the plane of the screen like that, and then we use a wedge to indicate that this is coming out at you, and a hashed wedge to indicate that that's behind the screen. So you imagine that this one is sticking out at you, and the other one is behind the screen. So it's 3-dimensional. The bond angles are going to be the same, and they're going to be 109.5 degrees, because that's what a tetrahedron is. Any questions?